Hi everyone, I'm Steve Tatarunas, Technical Support Manager at Listen Incorporated. I'd like to welcome you all to today's Advanced Microphone Measurements webinar. And we'll talk about what to measure, how to measure, and what does it mean. So the topics for discussion for today's webinar, we're going to open with a demo of microphone substitution, equalized source, and transfer function sequences using SoundCheck. And if you attended the first webinar, we briefly covered some of those sequences, but we really didn't show them in depth. We just discussed them in theory. And as we do this, we'll also talk about how to calibrate for these measurements and discuss the trade-offs involved in making them. Once we're done with that, we're going to cover several advanced measurements, including making polar plots, measuring microphone self-noise and signal-to-noise. We're going to do an open-loop microphone measurement, and then we're going to show a demonstration of active and passive noise rejection. So let's start with the standard test methods. And there are three standard methods for microphone test in SoundCheck. And the first one is the substitution method, where we measure a known calibrated microphone, otherwise known as our reference microphone, and then we measure the unknown microphone that we want to characterize, otherwise known as the DUT microphone, the device under test. And then we can use some post-processing to calculate the DUT microphone response and sensitivity. So let's flip over to SoundCheck and start with that demo. So as with most SoundCheck sequences that come bundled with SoundCheck, we have a sequence note here, and when I open the sequence, the note will open. It gives you an introduction to the sequence, shows you what you might expect to see on your final display, talks about the hardware requirements, how to calibrate and set up, and lastly, a quick system diagram. So what I'll be using here today is an Amp Connect. I actually have two microphones here, which I'll be using for a reference and a DUT. They're both SCM Listen microphones, and I've bundled them together so they're as coincident as possible. And then I have these mounted on top of a Brüel & Kjær mouth simulator. So that will be our test equipment setup for the first part of our webinar here. So let's run the sequence, and then we'll go take a look at the results, and I'll walk you through the sequence a little bit to tell you what it's actually doing. There might be a few prompts while the sequence is running to actually replace the reference mic with the DUT mic, but in this case, they're both already mounted here, so there won't be any sort of substitution involved. So we're prompted to make sure the microphone input is calibrated. I've already calibrated the reference mic, and it's placed in front of the mouse simulator, and I will now press continue. So we've captured the response of the mouth through the reference mic. Now we're going to test the DUT mic. And here's our final display. So what we have up in the first XY graph is the response of the DUT mic, and it's referenced to dB RE 1 volt per Pascal. So we can see that the response of the reference mic relative to the DUT mic is rather flat. There's a little bit of deviation up here above 6K, or actually probably around 3K. And we can clearly see that the sensitivity is about minus 34 dB. And then on the lower XY graph here, we have both the reference and DUT mic curves superimposed on each other. And you can see that we're actually using two y-axes here because our reference mic is showing up with its calibrated units, dB RE 20 micropascals, and the DUT mic is just showing up with our kind of unity units, dB RE 1 volt. Now if we open up the sequence, take a look at that, we'll see that there's a couple of message steps in here, one for telling you to calibrate your reference mic, one talking about the substitution. But otherwise, it's pretty straightforward. We have our stimulus step here. It's a very straightforward sweep from 10K to 100 Hertz at 10 millivolts RMS. We're actually using a direct output here, so we're not accounting for the gain of the amplifier. We're only telling the direct output to put 10 millivolts out into our amplifier. We have a standard play and record acquisition step, and then an analysis step where we're determining the response of the reference microphone. We have our prompt to switch out the reference mic for the DUT mic, and then a second acquisition step for the DUT microphone, and then the analysis of the DUT response. And then the last two steps are where we're actually determining the response of the DUT mic, and that's a simple post-processing arithmetic step where operand A is the DUT mic, operand B is the reference mic, and we're doing linear division, and the result of the step is called the normalized response, and that's what we're seeing up here on this larger XY graph. And then there's also a step here designed to determine the sensitivity of the microphone. So what we're doing is we're looking at that normalized response curve, have a search range set for a single frequency of 1 kilohertz, and the output of the step is going to be the 1 kilohertz sensitivity. And that's what we're displaying on this little table view here. So there you have it. There's a quick overview of the substitution method, and the only real calibration required for this is that you calibrate your reference microphone. Let's go back to our presentation and talk about the next method. And that's the transfer function method, and this is pretty interesting. It's similar to a substitution method, but we're not going to post-process the response curves. We're actually going to analyze the reference and the DUT waveforms. So once we've done our acquisition, the reference and the DUT recorded time waveforms are analyzed using a transfer function algorithm. And the transfer function is very flexible because it allows for the use of many different stimulus types. So we're not just tied down to using a swept step sine wave or a log sweep. We could use noise, music, anything in those cases. But for our example today, we're going to use a multitone stimulus, which is one of the options in SoundCheck. And the real nice thing about multitone is that we can do very, very fast measurements and get very accurate results when we're testing microphones. So again, let's pop back over to our SoundCheck. So let's run our sequence, and then when it's complete, we'll take a look at the results and a quick look at the sequence itself. So here's the transfer function using multitone. And as you can see, the acquisition step is very fast compared to the step sine sequence that we had just run previously. The duration of the stimulus was only 1 second, and in theory it could be made even shorter than that. So that's one of the beauties of multitone, is very fast stimulus and acquisition. And as we can see here on the final display, things look pretty much the way they did in the last sequence. We're displaying the response of the DUT mic up here, and then down below we have the spectrum of the stimulus and the response, the stimulus being the recorded time waveform of the reference mic, and the response being the recorded time waveform of the DUT mic, and those are the actual FFT spectrums of those two waveforms. So if we open up our sequence editor again, we'll see that it's a very simple sequence, only 4 steps compared to the previous sequence, which probably had upwards of 10. And we'll just take a quick look at the multitone setup. We have level, again, we're playing out through a direct out, so we have a very low stimulus level to account for the gain of the amplifier. Our frequency range is the same as the previous measurement, 100 hertz to 10K. And up here we can see the multitone waveform. Play and record, pretty straightforward, and then we have the multitone analysis step. And this is the only tricky part here, is that we want to have the reference mic recorded time waveform used up here as the stimulus, and the recorded time waveform used down here as the response. Otherwise, the setup is pretty straightforward. You can set up your analysis resolution over here. We are sticking with 12th octave. I'm using power averaging. With RMS scaling, we could use complex averaging over here if we wanted to use to get some phase information out of the measurement as well. So there's a quick look at transfer function measurements in the sequence. Let's go back over to our presentation slides and talk a little bit about the third method, which is the equalized source speaker method. So what we're going to do here is we're going to use the reference mic to equalize the source speaker. And there's a calibration sequence for that in SoundCheck that I'm going to demonstrate to you momentarily. And then once the mouth is equalized, we will use that to measure the dot mic. So let's go back over to SoundCheck. So what I need to do is open up calibration, go to the output tab and select the mouth simulator, and I'm going to select a calibration file for the B&K 4227 mouth. It's connected to output 1 of my hardware. I'm going to do a speaker equalization calibration here, so that's been selected from the drop-down list, and my input signal path is going to be the reference microphone. So now that this is all configured, I can click on Calibrate Device. There's a prompt to tell me to make sure that the microphone input has been calibrated, and then just a recommendation for how to place the reference microphone. So when I press enter, you're going to hear a brief 1 kilohertz tone, and we'll be using that to calibrate the sensitivity of the mouth. And if the sensitivity falls within an acceptable limit, SoundCheck will prompt me for a start and stop frequency for the equalization of the mouth. But before we do that, we want to enter the test level for the calibration. And this is pretty important because we know that loudspeakers aren't necessarily the most linear transducers in the world, and their response at 80 dB might be quite different from their response at 100 dB. So we want to make sure that the equalization that we're going to be applying to the loudspeaker is appropriate for our playback level. So in this case, I'm going to go with 94 dB, which is what we'll be using in the sequence subsequent to the calibration. So if I click OK here, you'll hear the 1 kilohertz tone. So we're going to equalize down to 100 hertz and up to 10K. And after I click enter here, you'll hear a sweep. And so here we have the response of the mouth relative to a 94 dB at 1K output from the mouth, and we've normalized that response to 1 kilohertz. And as it says down below in our little text box, the graph shows the response of the speaker. It's within the recommended tolerance. And the tolerance here is actually pretty wide. You can see our upper and lower limits, and those are essentially plus or minus 20 dB. So there's a lot of leeway here in terms of what we feel is a safe range for applying an equalization to a loudspeaker. And in this case, the mouth falls well within those limits, so we're in very good shape. So the next step is that we're going to apply the equalization that we've created in SoundCheck to the stimulus and then play it out of the mouth one more time. So there's our first pass at equalizing the mouth. It's pretty good. It's not perfect. There's a little kind of a hiccup down on the low end and a couple spikes up around 2K. So what we can do is we can do another iteration of this equalization. And what's going to happen here, we're going to actually take this leftover bit of non-flatness, apply it to the EQ curve, reapply the EQ curve to the stimulus, and then go through this whole equalization process one more time. So by pressing enter, we can do that. But first there's a prompt, is the EQ'd response flat enough? And it isn't. If I said yes, we'd accept the EQ, exit the sequence, and proceed with our measurement. But in this case, we want to do it one more time. So there's the next pass. You can notice that it's noticeably flatter than the previous attempt. So we're heading in the right direction. And let's go through this routine one more time to see how flat we can get it out in this environment, because there's certainly some reflections here. So I think we can get rid of a few more of those. A little bit better, and considering, we're in this room, there's a lot of live surfaces around us, that's probably about as good as it gets. If you were going to be doing this sort of equalization in an anechoic chamber, or maybe a Brühl and Kjær anechoic box, you'd see that things can get pretty flat in a very non-reflective and quiet environment. So this looks good to me. I'm going to click yes, and I'm going to save. And what happens at this point is that the equalization and correction curves are now saved into the memory list over here. We can see that the B&K 4227 mouth curves are over here. We have our EQ out curve, and we also have our correction curve, which was just that little bit of non-flatness that was left at the equalization. And when we finally come around to using this calibration in a sequence, we'll be applying the EQ to the stimulus itself, but the correction curve is actually applied in the analysis step as a bit of post-processing. Okay, so let's call up the sequence called microphone. It's a basic example of one of the two most common measurements. We determine the frequency, response, and sensitivity of the speaker playing an equalized sine wave from 10K to 100 Hertz. And again, it's the standard sequence note format, so we're all familiar with that, and we won't go through the whole thing. So let's, once again, run the sequence. We'll take a look at the results, discuss those, as well as the sequence itself. Okay, so here's the final display of the microphone sequence. Our top XY graph here is labeled response. That's the fundamental, and it's showing the sensitivity of the speaker in these units of dB RE 1 volt per Pascal over here. So we're down around minus 34 point something dB, which jives with the measurements that we've made previously. And down here we have what we call the aligned fundamental, where we've taken the response curve, aligned it to 0 dB at 1K, and applied some limits to it. The limits in this sequence are arbitrary. You could set them any way you want to, but in this case it appears that they're set to about plus or minus 3 dB. So, do with the limit step what you will, but let's again open up the sequence editor and take a quick look at this. So here we have the stimulus file, and as you can see when we open it up, you can see the effect of the equalization on the waveform, right? It's not a perfectly linear waveform with the same level at all frequencies. So clearly there's being some EQ applied to the waveform, and we enable that by using the Apply EQ checkbox down here. Otherwise everything is pretty much the same. We prescribe our test level here, 1 Pascal RMS, the start and stop frequency of the sweep, so everything else is pretty straightforward. We do a play and record, we do an analysis, we do a curve average to find the sensitivity. We take the fundamental, average at 1K, determine the sensitivity. And then we have a limit here for sensitivity. Upper, lower, it's 19.9 millivolts per Pascal translated into those more linear units. So this passes no problem. and then we have our limit on the microphone response, and it's a floater, so if I hit apply, we can see that it's well within the upper and lower limits. So in this case, it's a good microphone. So there's a quick overview of the 3 common microphone measurement techniques in SoundCheck. So now that we've demonstrated the 3 standard test methods, let's take a moment to discuss some of the trade-offs and other considerations. So all of these methods require that the source speaker be stable. So it should have a stable frequency response that doesn't change over time due to heat, humidity, other changes in environment. If your speaker isn't stable and you've calibrated and it starts to drift, then your measurement confidence is going to go down. So I think the point here, and that we'll keep reinforcing, is that a really high quality source speaker is the way to go when you're making microphone measurements. The equalized speaker method has the advantage of uniform level at all frequencies, but it can push the speaker harder and perhaps closer to instability if there are frequencies when lots of equalization are being applied. Substitution method, on the other hand, might allow for the source speaker to be used over a wider frequency range. Because we're not EQing it, we can just use an unequalized response to compare the reference mic and the DUT mic. The only consideration here is that at the low frequencies and very high frequencies where the speaker might be rolling off, we have to be careful that we're not measuring into the noise floor of the room. So just be aware of the environment that you're testing in with respect to upper and lower frequency limits when using the substitution method. A speaker that has a relatively flat response is preferred as opposed to one that has a lot of response peaks and dips. And really, lastly, microphone position is critical. It has to be stable in order to get accurate, repeatable results. A lot of manufacturers use very rigid fixturing that always guarantees that the microphone and the source speaker are going to be in the same place. Other people might use lasers to help precisely position the microphones and the source speaker. So whatever works for you, but there's a couple of the most typical approaches is having a very rigid fixture or using some sort of laser positioning. Our next topic is polar plots. So the intent of a polar plot measurement is to measure the directional response of a microphone. And we talked a lot about microphone types and microphone patterns in the previous webinar, so I hope you remember some of that. And in order to do this measurement, we're going to need a turntable, and we mount the microphone on a turntable and we rotate it in predetermined increments relative to a calibrated source speaker. And we start directly on the axis of the source speaker with a microphone pointed at it at 0 degrees. We start by measuring a reference mic at 0 degrees, and then we substitute that with the DUT mic. And we get 3 important results out of this sequence. We get the polar display, we get a directivity index, which is a curve, and a directivity factor, which is a value. And over here, we can see a little schematic of the setup diagram. We have our turntable, we have a DUT mic, a reference mic, we have possibly some sort of phantom power for our DUT mic. We have an audio interface and an amplifier for our loudspeaker. Now, I don't have a turntable here, obviously, and it would take quite a while to demonstrate one of these sequences in action to run it from start to finish. So what we're going to do today is just use some recall data and look at a couple of different microphone types and the types of results we might expect if we had actually measured one of those. One important consideration too in the setup of the turntable is that you want the acoustic center of the microphone to be aligned with the center of the turntable. So most microphones have on their turntable, or their platter, if you will, they have various mounting positions and bolts, so you can easily take your microphone stand, and in this case we're showing some sort of a boom stand, so we have some control over the height and location of the microphone relative to the center line. So any common turntable will allow you to have this type of bolt down so you can properly position the microphone. But it's really critical that the acoustic center of the mic be at the center of the turntable in order to get the proper measurements, and also on the center line of the source speaker. So very important to follow the setup instructions as shown here in this hardware setup. So let's open one of our mic polar sequences here, and as you can see from the sequence note, this one's designed to be used with the outline turntable. We have another version of this sequence that's designed for use with the Linear X LT360. The sequence note's pretty straightforward, as the intro tells you the purpose of the sequence, shows you a screenshot of the final display, lists the software requirements. In this case, they're pretty important. You need to have the time selective response module because we are using the substitution method and making simulated free field measurements here using time selective response analysis. And obviously, you also need the polar plotting module enabled on your license and able to run this sequence. Hardware requirements are straightforward. You need a turntable, a good quality monitor, be it powered or passive, power amplifier if you don't have a powered monitor, high quality reference mic like the Listen SCM, and an audio interface. What follows are just some instructions for setting up the outline in order to have it communicate properly with your SoundCheck machine, and then down below hardware setup and calibration and a familiar looking hardware diagram. So let's take a look at the sequence, and then we will not necessarily run the sequence. We're going to recall some measurements that we've made previously and just talk about the final display. The sequence begins with a hidden message step that establishes the start time for the TSR window, and by default that's -2 milliseconds. You can edit that if it doesn't work in your environment, but it's a pretty good starting point. The next is a message step asking if you'd like to recall some previously stored data. We'll be using that momentarily. And then just some user prompts. Set up your reference mic, make sure the turntable's at 0, and there's the outline step here that will return the turntable to 0 if it's not there. The next step will set up the stimulus level, and in this case I'd like to test it 94 dB. An operator message follows, and then the stimulus step here. We can take a quick look inside of the editor, and we can see that our 94 dB value from the message step is now carried into the stimulus editor, and that's going to be our test level. Our sweep rate is here. Our start frequency and stop frequency are here. And we are using a calibrated source speaker, but we're not using any equalization, so the EQ checkbox is disabled at this point, but we are using the calibration so we can define our stimulus level in dBSPL. And as you recall, we don't use EQ when we're doing the substitution method, which is what we're using in this sequence. Okay, step 9 is play and record acquisition, and that's followed by our first TSR analysis step. And what this step does, it has a very wide window, and it outputs an impulse response using that very wide window, and we pass that impulse response through this post-processing scaler step where we look for the maximum of the impulse response from 2 milliseconds to 20 milliseconds, and this should capture the first strong reflection from any room boundaries. And we name this value first reflection, and we use it in a subsequent polar analysis step where we have our start time, and then we pass that first reflection value into the step from the memory list here. Oh, and one more thing of note, at this point we do have our curve that's called reference fundamental, because up to this point we've had the reference mic mounted on the turntable. And at this point There's a message step saying replace the reference mic with the dot mic. And then we move into this loop where we'll be measuring the polar response of the dot mic. So what's going to happen here is we're going to go through this loop 18 times, and after each iteration of the loop, we're going to move the turntable in 10-degree increments. So we'll wind up with 18 measurements from 0 to 180 degrees, and when it comes to the end of the sequence and time to display the data, we can actually tell the final display to mirror the 0 to 180 degree curves to fill in the 180 to 360 points on the polar display. So let's take a look at what's going on inside the loop quickly. We have an acquisition step measuring the dot mic. We have a TSR analysis step here. Our time windowing has been set up previously in the sequence, and we're going to generate a curve that's called last fundamental. There's a limit step here. It's just a little housekeeping. It's keeping track of the turntable position. And then we have a post-processing step here where we're taking our last fundamental curve, we're adding a 0 to it. So in essence, all we're doing here is this just a step where we can rename last fundamental to a curve called on-axis response. Now we do another post-processing step where we take our last fundamental, which is the dot mic curve, and the reference fundamental, which we measured earlier in the sequence, and this is the actual substitution step here. And this gives us a curve called dot frequency response. There's a limit step here where we're going to align the data to 0 dB, and then a couple of sensitivity post-processing steps where we're calculating the sensitivity of the dot mic in both linear and log dBV and millivolts per Pascal. Now we have a normalization step, another post-processing step where we take the last fundamental and divide it by the on-axis response. And this gives us all of the normalized curves over here that we see in the memory list. So every time we go through the loop, we're creating one of these normalized curves, and every time we go through the loop, we'll also be appending the curve name with the angle of the turntable at the time of the measurement, so 0 through 180 degrees. And we're getting all of these from the loop index, which I'll show you momentarily. Next, we're taking last fundamental, and essentially here's another rename, and we're calling this fundamental. And again, these will all be saved into the memory list as the fundamental curves prepended with the measurement angle. As a limit step here, again, just housekeeping with the turntable to keep track of the position. A outline step for moving to the next angle. A display step inside of the loop here, and then the end of the loop. And some of the loop logic is in here. So this is where we set up the logic at the end of the loop. We jump on pass back up to the top to the dot mic acquisition step. And this is where we establish the loop index. So we start at 0. We have 10 increments. The increments are in degrees, and the name here is angle. So that's how we get all of this data to be prepended to the curve names over here. So after we've gone through the loop, after we've collected all of our polar data, we calculate the directivity index by taking all of the fundamental curves, selecting them, and these come out as the directivity index. There's some information we need to fill out down here in terms of the incrementation and the total rotation. And once we fill that in, we'll get our directivity index curve. And then there's a post-processing step here to calculate the directivity factor. One last outline message step, which returns it to 0, and then the final display. So let's run the sequence. Let's recall some data and take a look at the displays. I'm going to recall some previously measured data for a cardioid microphone. And here we see the final display. Let's close the memory list and let's minimize the sequence editor so we can take a closer look here. So as you can see, we actually have two polar displays here. We've decided that we're going to display the low frequencies on one and the high frequencies on another. So on the upper polar plot display here, we're displaying the frequencies of 125, 500, and 1K, and then down below 2K, 4K, and 8K. The displays are easy to configure. You go to the display menu, select preferences, and this is where we have our polar plotting options. Visible section, we can show different quadrants or halves or the entire polar display by selecting one of these controls. In this case, we've selected the mirror option because we're only measuring 0 to 180 and we want to mirror that data on the other half of the polar display. We can control our grid colors, the polar plot line width. Down here is where we determine the frequencies to display and the colors that they will be displayed in on the polar display. So in this case, our 125 polar is mapped to a color of green. If we wanted to change that, we could simply click on the color here and select something from the color map. We can easily add frequencies. So in this case, I'd like to add a 2K polar up here, and by updating, I can see that I've got my 2K data now included on this graph up here. And we can also delete data. So let's remove that. Lastly, there's the scaling options up here. At this point, we're scaling from 0 to minus 30 dB. And we've entered this value manually. If I wanted to auto scale, I could do that and simply click the update button and you would see the scale over on the graph change. And now it's auto scaling to the data over a range of 0 to minus 21. But let's go back to manual. Update, and click OK. So aside from the two polar displays, we have the aligned frequency response. It's the response curve aligned to 0 dB at 1K. We have a couple of tables down here. The first one is displaying the sensitivity of the DUT mic in a couple of different units, dB, RE1 Pascal, and volts per Pascal. The second table here shows the directivity factor, and our last XY graph down below here shows the directivity index that we calculated in that directivity index post-processing step. So there's a quick look at polar plotting. Our next topic is self-noise, how to measure it. So the process is like this. First, we measure the equivalent input noise with the mic input shorted. And that's the current configuration of the amp connect here. And then we measure the microphone self-noise. So these are essentially two spectrum measurements. And then we display both the noise spectra plus the equivalent input noise and the self-noise values on the final display. And the important thing is to have the DUT microphone mounted in an isolated enclosure like this B&K 4232 here, or inside of an anechoic chamber. But definitely one of the prerequisites here is to do this in a very quiet, controlled environment. So let's go back over to SoundCheck, and let's run our sequence. So this sequence gives you the ability to recall stored preamp measurements. So if you need to measure a series of microphones, there's no sense in measuring your preamp noise over and over again. So there's a nice little benefit to the sequence. But in this case, we'll click no, and we will actually remeasure the preamp. There is no gain on the preamp. There's 0 dB, so I'll click OK here. And I do have a 150 ohm load across the input at this point, so we'll click OK. And I will replace the microphone input noise file, and there's the input noise spectrum, or what would call the preamp equivalent input noise. So we'll press enter to continue, and it's going to prompt me to remove the shorting plug and to connect the microphone. So I'll just do that now so we can get the microphone warmed up before we make that measurement. I'll press enter, connect the mic under test to the power supply, and place the unit in an acoustically isolated enclosure, which it already is, so I'll press enter here. And there's the microphone self noise. It's asking me if I'd like to enter the sensitivity value. Why not? And I'll do that in millivolts per Pascal. And it's 15.6. And the noise of my microphone is not high enough. So it's nice to have a quiet microphone because it's barely above the noise floor of the input itself. So as you can see here, in the final display, we have the equivalent input noise in blue, and then the orange spectrum is actually the microphone self noise. So down below, a certain level, it's starting to poke its head up above the noise floor, but generally it's pretty close to the noise floor. The other information that will display on the final display here is the preamp equivalent input noise, the microphone self noise in dBV, and then the self noise of the microphone expressed in dBSPL, and it's down to about 25 dBSPL. We also show the corrected waveform here, and we show some information about the waveform over in this table, the transient peak, where it occurs, and what's the actual crest factor. So if there's any severe transients in the waveform, it's an indication that you might want to try to make another measurement or check out all your lines and cables, because maybe there's some other interference there. So there's microphone self noise, and we're going to continue into the next section here. Let me go back to my PowerPoint presentation, and moving right along, we're going to take that one step further, and now we're going to measure microphone signal to noise. And it's similar to what we just did, but we're going to add another component here where we're actually going to introduce some signal into the measurement so we can make a signal to noise measurement. So we measure the DUT mic self noise, analyze that, and then 1 kilohertz tone at 94 dB SPL. Then we calculate the A-weighted spectrum for both of these measurements, and we power sum the self noise spectrum, and then we calculate the DUT sensitivity at 1K from the signal spectrum. And then from all of these spectra, we can calculate the DUT signal to noise ratio, equivalent noise level as well. And the equivalent noise level is the test level minus the DUT mic signal to noise. So let's run our sequence, and then we'll take a look at the results and the sequence. I don't have any preamp gain. I've connected the mic under test, and I have calibrated the source speaker. Probably won't hear any sort of stimulus because the box is pretty well isolated, so we'll have a bit of silence here while the sequence runs. And here's our final display. So if we take a look, we have a couple spectra here. We have the self-noise spectra, which is the orange curve, which is kind of buried underneath here. And then we have the signal spectrum, where we have the 1 kilohertz tone. So looking over here, it tells us that the DUT mic self noise is about 95.2 dB down A weighted. The DUT mic signal is at minus 36.1, so that yields a signal to noise ratio of 59.1. And then we also get the equivalent noise level of 34.9, which is the difference between the signal to noise and the actual signal itself. So there's a look at our measurements, and the sequence itself is pretty straightforward. We have a prompt to enter our test level. We have our 1 kilohertz stimulus. We are recalling some weighting curves and entering our preamp gain. Our first acquisition is record only, where we're just recording the microphone noise. We do a spectrum analysis on that and A-weight it, and any gain correction to compensate for whatever preamp gain that we're using. In this case, there wasn't any. And then we power sum the corrected and weighted curve. The next acquisition step is actually play and record, where we're playing back the 1 kilohertz tone. Again, we analyze that, take an average at 1K. Then we have another preamp gain correction and a calculation for the DUT signal to noise ratio and a weighting of the DUT mic signal, and then more correction. And we do a level conversion from Pascal to dB/SPL and a final calculation for the equivalent noise level. So there's a quick look at our microphone signal to noise ratio sequence. Our next topic is open loop measurements. And open loop measurements are required when the DUT mic is embedded in a portable or standalone device where the signal can't easily be returned to the measurement system in a closed loop. So for instance, this tablet here, your cell phone, anything that has a microphone embedded in it. But if the device has the capability to record, then we're in luck because we can make a recording on the device and transfer that recording back to SoundCheck. So the procedure here, the process is that the stimulus is played through a calibrated source speaker. It's recorded on the portable device, and then the recorded waveform is transferred back to the SoundCheck computer for analysis. And here's a little schematic of how this might work. We have our recording device over here, our source speaker, and our amp connect. And so the signal comes out of the source speaker, recorded on the device, and then transferred somehow back to SoundCheck. Now, in order to do open loop testing, there's a number of post-processing steps required because the stimulus and the response waveforms may be at different sample rates, and that's actually the case in this particular measurement here. The tablet's going to be recording at 48K, and the amp connect is operating at 44.1K. So what's going to be required here is that the waveform that's coming in from the DUT should be resampled to match the stimulus. And to take that one step further, after we do the resampling, the waveform should also be frequency shifted to account for any remaining small sample rate errors, because there could be some slight differences in the clock speeds on the test system and on the device under test. So that's always a good habit to get into. Now, previous versions of SoundCheck before SoundCheck 18.1, which we're using today for all of our demos, required waveform windowing if the delay in the recorded time waveform was greater than 1 second. In other words, if there was a gap between the start of the recording and the actual presentation of the stimulus to the device under test. But there's a new feature in SoundCheck 18.1. It's called Auto Delay Plus, and it's delay agnostic, and it requires no waveform windowing, which really simplifies these open loop microphone sequences. In prior versions of SoundCheck, you had to do a lot of post-processing to find the start of the waveform, determine how long it was, where the end was, and then passing it through a windowing step to remove any excess delay at the beginning of the waveform. But don't have to do that anymore. So Auto Delay Plus is a real great benefit for people like me who are about to do an open loop microphone measurement. Okay, so let's run the sequence, and there'll be some prompts along the way. And at some point, I'm going to have to transfer the waveform from the tablet up to the cloud and down to the computer. So there'll be a little bit of time where we're just moving some files around. This recording program saves to Google Drive, so that's what I'm actually going to be using today. So I'm going to begin recording on the device. Press the record button. I'll let a little bit of time pass before I continue so we can have some lengthy delay at the start of the recording. And press enter to continue. And stop the recording and transfer the file to the computer, and the file must be in WAV format, which it is. And what I'm doing here is uploading the recorded time waveform from my tablet to Google Drive and then downloading it to my SoundCheck PC. Now I'll press enter to continue, and what it's going to do is prompt me to select the file that we just downloaded. My downloads folder, here we go. Press OK, and then at this point we'll bring the waveform into SoundCheck, we'll resample it, we'll frequency shift it, and then we'll do some analysis and display our results. And there we have it. Up here in the top XY graph, we have the microphone response. Down below is the recorded time waveform. A little bit of noise here before we actually presented the stimulus, but it didn't seem to create any issues with the analysis. Auto Delay Plus identified the recorded part of the waveform just fine, and we have a results window up here that shows us the calculated sensitivity at 1K. It's a little bit less than minus 20 dB RE1 full scale per volt. And let's just quickly take a look at the sequence itself. So there are some operator prompts in here, but really, we have an acquisition step that's just playing back the stimulus, and then the operator message to transfer the file to the computer. Once it's there, we have a recall step, and then we go through the resampling step, where we have our recorded time waveform. It comes in at 48K, we resample it down to 44.1, and then we take that resampled waveform and pass it through our frequency shift. So operand A is the recorded time waveform that's been resampled. Oops. And then our reference frequency comes from the stimulus waveform. Once we do that, it's just a simple matter of fundamental analysis, so we can get our fundamental curve, and then we do a curve average to derive the sensitivity. And there's a limit step there for sensitivity, and there's one for response that we're not actually showing the limits here on the graph, but that's baked into the sequence. So you can find an earlier version of this sequence in your SoundCheck install, and we'll be updating it in future versions of SoundCheck so you can take advantage of the Auto Delay Plus feature. And that's a quick look at open loop microphone. So the next topic we're going to cover here is microphone noise rejection. And as you can see, we've brought in some additional hardware for this particular demonstration. So we've got our hats, we mounted a communications headset on it with a boom microphone, and we have a couple of small speakers on each side that we're going to use to generate a noise field around the hats and the microphones as part of this test. So the test characterizes the noise rejection capability of, in this case, a communications microphone. And we start by measuring the ambient noise spectrum in the room using the reference microphone. Next, a signal output, the speech, is played from the mouth simulator and recorded using our calibrated reference mic at the mouth reference point. Then we use a noise output, which is the pub noise, and that's played from one or more source speakers and recording, again, using the calibrated reference mic at the mouth reference point. Next, we do another ambient recording using the DUT microphone, and then the signal and noise acquisitions are repeated using the DUT mic to yield the signal input, which is the speech, and the noise input, which is the pub noise. Once we've done all of that acquisition and analysis, we do some post-processing where first we calculate the signal gain by subtracting the signal input from the signal output. And then we calculate the noise gain by subtracting the noise input from the noise output. And then finally, the signal to noise spectrum is calculated by subtracting the noise gain from the signal gain. And the reason that we're measuring the ambient noise in the room with both microphones is that for the best accuracy, the signal and the noise spectra should be at least 5 dB above the ambient noise floor of the measurement environment. Okay, so it's time to flip back over to SoundCheck. So when we open our sequence, we get our sequence node here. It's a standard sequence available on the Listen website. Gives us a brief introduction describing what the sequence does, shows us the final display, talks about the different software requirements. This does require RTA module and wave file equalization and a bunch of different hardware, either a head and torso simulator or a mouth simulator. We'll need a reference mic and some amplification for the noise speakers, as well as for the mouth simulator. We talked through the calibration and the hardware and the setup, and here's just a basic diagram of what I have next to me. In essence, is the hats, a couple of powered speakers, a reference microphone, and another amplifier to power the mouth. Okay, so let's run the sequence now. During the sequence run, there'll be a couple of sections where we're just recording ambient noise, so you'll hear nothing but silence for about 13, 14 seconds. And you'll also hear the speech played back twice, once for the reference mic, once for the DUT mic, and the same with the noise playback. That will also occur twice.
The shelves were bare of both jam or crackers. A joy to every child is the swan boat.
The stems of the tall glasses cracked and broke. The wall phone rang loud and often.
The DUT mic is already in position, so we'll just press enter to continue.
The shelves were bare of both jam or crackers. A joy to every child is the swan boat.
The stems of the tall glasses cracked and broke. The wall phone rang loud and often.
Okay, so let's take a quick look at the results. The first XY graph here is the signal output, and that's the ambient noise here in purple that was recorded with the reference mic. Then we have the noise output here, and then the signal or speech output here. The second XY graph is the signal input that was recorded by the DUT mic. And again, from working from the bottom up, we have the ambient noise recorded by the DUT microphone here. We have the noise input here and the signal or the speech here. And so in the end, we wind up with this curve, which is the signal to noise spectrum that tells us exactly, how much, or it shows us the ability of this microphone to reject noise at different frequencies. So down around 100 hertz, based on all the calculations, is able to reject about 12 dB of noise, and that attenuation gradually decreases as the frequencies increase it. But even up around 2K, there's still a bit of attenuation going on. So generally, this is a pretty good microphone, not great, not horrible, and the results are pretty believable based on my experience with it. So there you have it, a quick look at how to measure microphone noise rejection. And again, this sequence is available on the Listen website for download. So before we wrap things up today, I wanted to give you a little preview of Advanced Microphone Measurements Part 2 and what some of the topics might be. One of the important things when it comes to measuring microphones these days is measuring microphone phase, and that has a strong tie into microphone arrays, and the use of microphone arrays is becoming more and more prominent in the world around us. So these two topics tie in nicely with each other, and we can have a very thorough discussion about those. There's also an opportunity to discuss MEMS microphones and how to measure them, so we'll give you a good demo of that and the related equipment, and we'll do a high-level overview on distortion. We will be doing a webinar later this year where we cover distortion in depth, so we'll just talk about a couple of techniques here quickly. So we'll be covering these 4 topics in Microphone Measurements Part 2, so there's something for you all to look forward to. So that brings us to the end of today's webinar. Thank you all for attending and for your attention, and we'll now open up the floor to any questions that you might have.